Hello, thanks for coming today. I'm Sophie, a second year PhD student at the University of Cambridge. I'm going to be talking today about the insights the UK's oldest rocks can provide regarding the evolution of the Archean crust. Archean outcrops across the world expose different structural levels of the crust. There's a broad split in outcrops between those thought to represent the upper crust, often referred to as granite greenstone belts, and those representing the mid to lower crust, which are generally more homogeneous than upper crustal blocks and are mainly made of tonalite-trondhjemite-granodiorite, i.e. the nicer to say TTGs. In most Archean areas at all crustal levels, we observe rocks that are interpreted as having supracrustal or shallow origins juxtaposed against rocks from a deeper structural level. The occurrence of these rocks has been used as evidence of Archean tectonic processes, and the figure here shows some of the ways that these rocks could possibly be generated, ranging from uniformitarian subduction on the right to non-uniformitarian sagduction on the left. Sagduction is the process I'm specifically interested in here and has been widely discussed as a way to move shallow rocks to depth by the shallow rocks sagging into the lower crust through a density instability. In this study, we develop a numerical model of sagduction as a density-driven settling process, and we use a test case from northwest Scotland to show how the model can be used to constrain sagduction viability in a specific region. In this talk, I'm first going to go through the information I get from studies conducted on the rocks in northwest Scotland, and then I'm going to show how I use that information in a numerical model to work out whether sagduction scenarios are feasible. Firstly, to give a quick overview of Archean rocks in the UK, the UK's oldest rocks are the Lewisian rocks of northwest Scotland, coloured here in blue, and they're about 3 billion years old. The rocks that reached the highest pressure temperature conditions reached granulite facies conditions with temperatures in excess of about 750 degrees. These are highlighted in the box on the figure on the left and are in dark blue, and are zoomed in on the figure on the right. This region of the Lewisian is called the central region, and it's relatively uniform, mainly made of TTGs. However, the TTGs do contain occasional outcrops of other lithologies. These are highlighted on the map and are what people have interpreted as possible supracrustal assemblages. These lithologies are garnet-biotite felsic gneiss, mafic gneiss, generally comprised of garnet plagioclase and one or two pyroxenes, and ultramafic gneisses, which are often associated with mafic gneisses, which are comprised of pyroxene and olivine. To carry out this study, I needed to assess the differences in mineralogy and density between the TTGs and the possible supracrustal rocks at peak metamorphic conditions. I used existing databases of samples to represent the TTGs, the mafic gneisses, and the ultramafic gneisses. These sample locations are shown by the blue and grey dots. In addition, I got my own garnet-biotite felsic gneiss samples and one mafic sample from Knock-and-Sivian. Knock-and-Sivian is shown in orange on the map here, and it's the largest possibly supracrustal body in the Lewisian. Firstly, to find maximum pressure temperature conditions reached in this region, I initially focused on that mafic gneiss sample I collected from the Knock-and-Sivian region. As out of the rocks in this region and in the central region more generally, the mafic gneisses best preserve the peak mineral assemblages. The figure here shows a typical field of view from the mafic gneiss in plane polarized light and ChemScan, and the peak assemblage was interpreted as being 2-pyroxene, garnet, plagioclase, ilmenite, and a melt phase. The field that contains the peak assemblage on this pseudo-section is highlighted. Additional constraints from garnet chemistry give peak pressure temperature conditions of about 8 to 10 kilobars and 900 to 1000 degrees Celsius. This estimate is consistent with estimates of peak PT conditions compiled from mafic gneisses across the central region in a previous study by Faisal. And that's shown here on the right with the results from this study overlaid. Additionally, we can consider what water content is required to stabilize the peak assemblage. And this is done by making TH2O and PH2O pseudo-sections, which show that the inferred peak assemblage, highlighted again in black, is only stable at low water contents, supporting the general idea that the Lewisian was near anhydrous at peak conditions. So, going forward, we take the peak pressure temperature conditions that we've calculated here as representative of peak pressure temperature conditions across the central region. We then carried out phase equilibrium modelling on the rest of the samples with the specific aim of working out their mineralogy and density at these inferred peak conditions. These pressure temperature diagrams are representative diagrams for the other lithologies considered. I will note that the assemblages observed at peak conditions don't necessarily perfectly match the minerals we see now, as particularly the TTGs and garnet-biotite felsic gneisses are somewhat more prone to retrogression than the mafic gneisses. The ultramafic gneiss does have a similar assemblage, but it's not particularly useful in pinning down a specific pressure temperature field, given how little the stable assemblages change over the range we're considering here. Overall, by doing this modelling for all samples considered, we can build a picture of mineralogy at peak conditions, which is summarised in the figure here, where the minerals stable at peak pressure temperature conditions for each sample and their volume percent is shown. TTGs are shown in blue, garnet-biotite felsic gneisses in orange, mafic gneisses in grey, and ultramafic gneisses in purple. The results of this modelling can be further summarised by considering what the average volume of each mineral is for each lithology considered. A key outcome here is that quartz and feldspar are very clearly the dominant mineral in the TTGs. And when we're looking at the other lithologies, they become increasingly rich in pyroxene, garnet, and olivine as silica content is reduced. Densities in the peak pressure temperature window can also be calculated for each sample. And as shown here, again, coloured by lithology, with lines denoting an average density for each lithology. These averages are summarised in the table on the right, just so you can see the numbers. This density modelling is useful because in our model of density-driven settling, we want to know what the density contrast is between TTGs and non-TTG lithologies. These contrasts vary from 0.11 to 0.56 grams per centimetre cubed, with the larger density differences representing the more mafic lithologies. The evolution of density difference over pressure temperature space can also be assessed. Peak conditions are highlighted by the grey box, and we have figures here shown for evolution of density difference for each lithology considered. The figures show that the density differences don't exceed the values calculated for peak conditions as pressure and temperature are reduced. We can now use the information that we've just got to provide constraints on a model of sagduction. Firstly, I'll just briefly outline the model used. To model sagduction, we have a dense layer overlying a less dense layer, giving a density instability. This instability develops into a solid particle falling through a viscous fluid. The particle is made of one of the non-TTG lithologies, and the viscous fluid is made of TTG. We model the particle as falling through Stokes settling throughout the whole sagduction event, as this is the fastest the particle could move, and the model is designed to give sagduction the best chance at succeeding. Using Stokes settling law, we can then calculate the stress on the falling particle and the strain rate in the fluid. From this, we can obtain the viscosity the TTG fluid must have to allow sagduction for a sagduction event with a specific set of parameters like the density difference between particle and fluid, the radius of the particle, the distance the particle has travelled, and the duration of the event. Having obtained this viscosity, we then use mineral flow laws to explore what temperature is required to give the TTG the required fluid viscosity. From the phase equilibrium modelling we did, we know the TTGs are predominantly feldspar and quartz at peak conditions, so the fluid behaviour is going to be controlled by the feldspar and quartz flow laws. So, from our fieldwork petrography and phase equilibrium modelling, we know the depth the particle reached and the maximum temperature it experienced, in addition to knowing the density and mineralogy of the fluid, the TTG. In the following model, we're going to vary the particle lithology the event duration, and the particle size to explore sagduction feasibility across parameter space. To start with, I'll just go through one iteration of the model. We have to choose a lithology, which sets the density difference between particle and fluid. We also choose a particle radius and an event duration, which will set particle velocity. From Stokes' settling law, we then obtain the fluid viscosity that would be required for the particle to sagduct. This viscosity is the black line on the graph. We then use mineral flow laws to assess how viscosity varies with temperature at the calculated strain rate. The different lines show different outcomes for quartz and feldspar flow laws. Quartz is shown in pink and feldspar is shown in purple. We also assess how water content may affect viscosity by considering both wet and dry scenarios. The wet scenarios are shown by the dotted lines and the dry scenario by the solid line. The intercept between the black line and each flow law is the average temperature that would be required during sagduction to allow the event to occur. We can then do the same calculations for different body sizes and event durations. Here just shown for a particle comprised of garnet-biotite felsic gneiss, with body radius increasing left to right and event duration increasing top to bottom. We can think about how feasible these scenarios are, given that we want to know what temperature and body size could give sagduction. Firstly, just considering a dry feldspar flow law, we can plot temperature versus body radius for the point on the graph where calculated viscosity intersects flow law, i.e. the temperature that would allow sagduction. We can do this for a range of timescales and body sizes, producing the following plot. We can then plot these curves for each possible particle end member and for all of the TTG relevant flow laws, noting that as TTGs are feldspar dominated, their behavior is best represented by outcomes closer to the feldspar flow laws than quartz. We can add constraints based on our observations of the Lewisian to define the relevant area in terms of temperature and body radius that we want to think about for the Lewisian. The largest possible particles in the Lewisian have radii of less than 5 kilometers. Temperature represents the average temperature throughout the sagduction event and is highly unlikely to be above 700 degrees. These constraints are shown by the red boxes. As such, we can see that sagduction is not particularly feasible in the Lewisian unless the lower crust is water saturated, i.e. represented by a wet flow law. And even here, there is a pretty narrow window in terms of temperature and body radius that would represent conditions seen in the Lewisian. Given that the Lewisian central region is thought to be fairly dry, our model suggests that the lithologies observed in the central region are possibly not best explained by sagduction, potentially implying uniformitarian tectonics is the best model to represent processes in this region. Thank you for listening.
So a question from Dick White. Sophie, how do you account for partial melting and rheology?
Yeah, that's a really good question. So in the model we're using here, we're basically just modeling the density and rheology of the melt-free component, so the restite component. So we're assuming, and you sort of see this in the central peak conditions, most of the melt has probably left, but we definitely recognize that the existence of melt would modify the viscosity of both our fluid and our particle, and there's questions to be raised about the timing of melt generation and potentially melt leaving the Lewisian with respect to this model, but it's sort of a first approximation as to how processes like these might be modeled in specific regions. But yeah, there's definitely scope to include more parameters. And yeah, melt is one of those that I'd say is a high priority.
Thank you very much, Sophie. That was an excellent talk.